All right, and once again, good morning and welcome to today's webinar on battery management systems and their role in safety and reliability. My name is Mark Musitano. I will be hosting today's webinar. With me on the line today is Chris Ewert from Ewert Energy Systems. This webinar is part of a two-part webinar series on batteries and it's a collaborative effort between DFR Solutions and Ewert Energy Systems. So we're very happy to have Chris with us today.
Okay, yeah, thanks. So my name is Chris Ewert. I'm with Ewert Energy Systems, and I primarily design battery management systems for large format lithium batteries. So battery packs like for electric vehicles or energy storage, that type of thing. So my presentation will focus a little bit more from that angle, but I will do my best to incorporate tips and material for consumer electronics, smaller electronics. A lot of the same principles apply. So in today's presentation, I'm going to go over following things. We'll start with what is a battery management system? Why would you use a battery management system? What can and can't they do? We'll spend a little bit of time talking about cell balancing. We'll talk about common failure modes, at least ones that battery management systems can do something about or detect, and then just go over some general design tips. So we'll start out with what is a battery management system? Battery management systems are most commonly used with lithium-ion batteries. You can use them with other types of batteries as well. But lithium batteries, you have to monitor each individual cell in series. And so because of that, battery management systems are most commonly used with lithium-ion packs. They often interface with other devices. They usually will provide some additional information. It might just be that they provide an on-off switch, but they might also integrate with a vehicle. You might need to know how much energy that you have in the battery pack, or the current limits, things like that, or state of charge. So they usually will integrate with some other devices as well. So the primary functions of a battery management system for lithium batteries, the most important one is over and under voltage protection for each individual cell. This is very important for lithium cells, and we'll talk about why in just a little bit. But that's the main thing. They will also generally provide thermal protections if the battery is getting too hot or too cold, and they will usually provide some degree of overcurrent protection. And usually, because the battery management system has the information about all the voltage of each individual cell and the currents going in and out of the battery pack, they're usually responsible for calculating the state of charge. Because they have all of that information, it's a more accurate way of determining the state of charge than just monitoring current going in or out externally, for example. They'll usually provide some level of cell balancing, and we'll talk more about that later on, and fault detection, and that would be detecting faults both with the battery pack, if there's a bad cell or something like that, as well as detecting faults with the BMS itself. Other functions of a battery management system that you may or may not find on one. Some battery management systems will offer current limit calculations, which is basically it's a calculation of how much current can the battery accept or provide at any given time. And there's a lot of factors that go into that, such as the temperature, the health of the cell, the state of charge of the cell, and the measured resistance from the cell, things like that. You'll often find some type of a digital or an analog interface to another part of the application. For example, if you have a cell phone, it's very helpful to know what the state of charge is, or it's helpful to know that your battery is dying and may need to be replaced. In an electric vehicle, obviously it's really important to know the state of charge, but you also, in a vehicle, you'd also need to know the current limits. How much energy can you pull if you push the pedal down? Some battery management systems will also provide health monitoring. They monitor each individual cell, and if there's an issue, it can tell you what's going on with the battery pack. This is generally a little bit more helpful for larger format battery packs, like in a vehicle or energy storage application where you might go in and replace a cell. And a lot of consumer devices, you may just want to know that the battery pack is bad and it needs to be replaced as a whole. It may not make sense to go in there for little cells and replace cells. Data logging and analysis is another thing that can be really helpful for automotive or for large format cells. Again, very helpful for being able to go in and figure out if there's something that's going on or if there's a problem, to be able to diagnose quickly what's going on. It's also very useful in consumer devices for being able to do, when you're doing research and development, to try and figure out what is the battery performing the way that you're expecting it to, and to look for various issues there. Some battery management systems will provide other calculations, range, time left, individual cell resistances. There's a number of different calculations that a BMS might perform. And they're sometimes integrated with other peripherals such as thermal management. If you have a large battery pack, or even a battery pack like on a drone, for example, where they may get very hot, you may need to have something that would switch on a fan or some type of other cooling system. In a vehicle, they're often combined with isolation fault detection. So if you have a battery pack that is isolated from the chassis of the vehicle or a stationary application, it's very helpful to know if you have a breakdown in isolation between the battery pack that's supposed to be isolated and the chassis, and that can help prevent more catastrophic external shorts, because it can detect if one short develops before a second one does, before it turns into something more serious. Okay, so why would you use a battery management system? And for lithium batteries, the main reason is that you have to monitor each individual cell voltage. And this is because lithium cells are extremely intolerant of overcharge and over discharge. If you overcharge a cell, even by a little bit, it will shave lifespan off of it. It can also pose a safety issue. Overcharge is something that can lead to thermal runaway. If it doesn't, it can lead to thermal runaway, but it can also do other damage to the cell as well, shave life off of it. Likewise, over discharge is actually also very important for lithium cells. You can actually kill an entire lithium battery pack in one single over discharge. And it's also something that if you overcharge a cell even a little bit, it can lead to lithium plating, which can pose a safety issue later on, and it also shaves life off of the cells. When you have a lithium battery pack where you have multiple cells in series, obviously when you run a current through that battery pack, each cell is going to experience the same current through it. And if you have one cell in the battery pack that has a higher state of charge, or it might even be that you have a cell that has a different capacity. So for example, if you take a cell or a battery pack where most of your cells are at 80% state of charge, and you have one that's at 90% state of charge, when you go and charge that battery, the cell that's at 90% state of charge is going to be the first one to reach its maximum voltage. And if you are looking at this strictly from a total pack voltage, a cell that's gone up, maybe 100 or 200 millivolts is not going to make a significant impact on the total pack voltage, but yet that cell is still going to be getting overcharged. Likewise on the discharge side. What can happen then? If you had a perfectly balanced battery pack where all of the cells are exactly the same capacity, exactly the same resistance, and exactly the same state of charge, in theory that wouldn't be a problem. Then you could use your pack voltages. But in reality, that never happens. Even the best balanced battery packs, there's going to be some minor differences in capacity. You're going to have some differences in internal resistance and internal self-discharge, so they're eventually going to unbalance a little bit. So in the real world, that just never happens. And one other thing to keep in mind, even if your battery starts out perfectly balanced and perfectly connected, perfectly matched, I should say, eventually the cells are going to age differently. And so what ends up happening in that situation is that you charge up and you get one cell that maybe it won't even turn into a more serious safety issue, but it will, the cell might get just a little bit overcharged, and that's going to shave life off of that cell. And then when you discharge the battery pack, you're going to have one cell that gets just a little bit over discharged, and that shaves life off of that cell. And what happens is the cell capacities change over time, and then you get a different cell that becomes your minimum cell, and you get a different cell that becomes your high cell. And what ends up happening is this problem kind of just spreads throughout the battery pack until the battery pack is destroyed. So which leads me to the second point: a battery management system that monitors the voltage and the health of each individual cell maximizes the cell lifespan by preventing that from happening. A battery management system can also go in and make changes to each individual cell's balance. So if you have cells that are a little bit too high, it can remove energy from those, or it can add energy to a low cell to keep them in balance. That maximizes, by balancing the cells, that maximizes the usable capacity of the pack. And we'll talk more about that a little bit later on. A lot of applications also need to be aware of the state of charge. As I mentioned before, a cell phone is very useful to know if you're about to run out of power, and a car, obviously, that's a very important thing so you don't get stranded on the side of the road. The battery management system is definitely the best place to do that because you have access to all of that information. Also, not all failures, but a lot of failures happen over time. You can see evidence that they're about to happen. And so a battery management system gives you some advanced warning that there's a problem, and it gives you a little bit of time to deal with that. And that's not true of all failures, but a lot of failures we see tend to be ones where you can see it coming. Another aspect of this, there's other limits that cells might have. For example, at various temperatures, every cell will have a minimum and maximum temperature that it can operate at. A lot of cells, so there's a lot of cells that can't be charged below freezing, for example. So a battery management system can monitor the temperature of the cell, and it can enforce what the maximum current limit is at any point. Some cells, even though they can be charged, let's say down to freezing, 0 degrees Celsius, it might be that when you hit 10 degrees Celsius or 5 degrees Celsius, you need to slow the charge rate in order to prevent lithium plating. So a battery management system can do that. There's other limitations. Some cells allow for pulsing. You can pulse at higher charge and discharge rates for very brief amounts of time. So there's other things that a battery management system can enforce. So this is, as mentioned at the beginning of the presentation, this is a two-part series. This slide is from the presentation part 1 that Vidju did, and she did an excellent job of describing some of the manufacturing characteristics of what can happen and what can lead to an elevated cell temperature, which then either turns into a benign failure where you may have a dead cell or a cell that has a lower lifespan left, or a damaged cell, or a cell that goes into thermal runaway and turns into a more catastrophic event. On the left-hand side, in the chart here, you can see different aspects that can lead to elevated cell temperature in purple, and different events that can lead to lithium plating. So a battery management system can help prevent a number of these, but not all of them. If there is a manufacturing defect with the cell, if there's metal contamination, for example, or damage to the cell, like physical damage to the cell itself, or something like that, a battery management system is not going to be able to do anything about that. But it can help with preventing overcharge, over discharge. It can help limit the operating temperature of the cell. It can enforce temperature limits. It can help with some external shorts, and it can also prevent low temperature charging as well. So those are some of the areas. In this presentation, if you'd like to get a copy of that, you can email Vidju at the contact email below, or her contact information will be available again at the end of the presentation. So focusing on the things that a battery management system can't do, as I mentioned, it can't protect against an internal short within the cell. If you get an internal short, the battery management system can detect that that's happening, but there's really nothing it can do. You can stop all charge and all discharge to limit that, but if a cell is shorted internally, it's going to be a problem no matter what. A battery management system also cannot extend the lifespan or the capabilities of a cell beyond the chemistry that it was originally designed with. It's not a magical device that makes everything work better. It can protect the cells, as I talked about at the beginning. It can prevent overcharge and over discharge, and it can maximize that life, but it can't make a cell provide more power than it does, or have a longer lifespan than it was originally designed with. It also, while it can offer some protection against shorts outside of the battery pack, beyond if you have an on-off switch for your battery, or a contactor, or some type of device that can shut off power from going in and out of the battery. It can protect to some degree against shorts there. If whatever the switch is has to be able to handle the fault current and to be able to handle switching the fault current. There also may be some timing related issues with that, so we always still recommend having fuses in there whenever possible, because that offers you better protection. But if you have a short that develops inside the battery pack before any type of switches, the BMS can again detect it usually, but it can't really do anything if there's no switch provided to shut that off. If you have a bus bar, for example, and you have it directly above a metal plate, and whatever is insulating it breaks, and the two terminals of the battery short against the plate, unless you happen to have some type of a switch in there, the battery management system is not going to be able to do much about that. So proper design is still important there. They also can't provide protection if they're not properly installed or designed or integrated. You can detect over voltage cells or under voltage cells all you want, but if the BMS has no method to shut off the load or to shut off a charger, it's not really going to do you a whole lot of good. All right, so we can talk about a little bit about some of the common failure modes that we see. So probably the most common failure modes are the first two, and they usually happen together. Low capacity, a cell that's maybe developed a lower capacity over time. Doesn't hold as much energy. It has lower amp hour capacity. Typically, that's also that also happens at about this in conjunction with a high internal resistance, and that would be basically if you're running a current through the cell, that would be a voltage that it would shoot up to when you've got a charge current going in, or go down to when you have a discharge current. You'd see a higher voltage drop and a higher cell with a higher internal resistance. So usually we see those two happen together when they happen, and that's usually a failure that develops over a period of time. We also see a lot of failures with cells developing high internal self-discharge, and that would be basically if you're leaving the cell with no load on it whatsoever, that it would discharge itself faster than other cells. There's a number of things that can happen with that. Most of those are internal issues with the cells, and that can lead to balance issues. And if you get a high enough internal self-discharge rate, that can also become a safety issue as well. Cell manufacturing defects, sometimes those can lead to slower, more benign failures. For example, a lot of cells have multiple, or would probably be more aptly named modules, because they actually contain multiple cells that are parallel together inside that single cell. Every once in a while we see a case where a bus bar inside comes loose and suddenly you've got a cell that has half the capacity and twice the resistance that it originally did. You might also see, but there's other cell manufacturing defects like the ones that Viju was talking about a couple of weeks ago in her presentation. Those can be more catastrophic, and they can, if it's a short circuit that occurs, it can just happen very quickly. Not a whole lot that the battery management system can do about those sometimes. Also, if there's other physical abuse to the cell, if you're using this in an automotive application, obviously the cells need to be able to handle shock and vibration, not just the cells, but also the connections between the cells. Thermal is a big one. If a cell is operating at elevated temperatures for long periods of time, that can take a lot of life off of the cell in a hurry. That tends to be an exponential function. The hotter the cell is, the more accelerated the degradation of life is. For an example of that would be with the Nissan Leaf, for example. They've done an awful lot of work calculating and testing the batteries, and for the most part that worked great. But they had a lot of vehicles that were being used in Arizona or other hot areas that were seeing premature battery capacity loss, and that turned out to be a thermal-related issue. Impact is another issue. Obviously, if the cell is physically damaged, that's going to be a problem, and certain cells need to be compressed. That would be something to check with the cell manufacturer on. This would be true more of large format prismatic and pouch cells than it would be with like 18650 or cylindrical cells, though. But that's a good thing to check with the cell manufacturer on, because the specs vary from cell to cell. So here's just a quick example of what a low capacity cell looks like. Pretty straightforward. There's two cells on this graph here, a red and a blue cell. And if they're balanced up at the top in this graph, and as you discharge, the red cell drops off before the blue cell does. You have to stop discharging the battery pack at the moment that the red cell reaches its minimum voltage, and because of that, the pack capacity is restricted to the capacity of the lowest cell. Here's a real-world example of a cell with a high resistance. You can see most of the cells are grouped together, and then as we apply a charge current to it, you can see the cells have various degrees of internal resistance. The yellow cells have a little bit higher resistance than, say, the green cell does. The turquoise cell is a bad cell. It's obviously got a significantly higher resistance than the rest. As we apply the charge current, the voltage goes significantly higher than the rest of them. And then when we remove the charge current, it drops back down to the bottom, kind of the bottom of the rest of the pack there. This particular example is likely a cell that also had a low capacity. As you can see on the left-hand side, it started out at a lower voltage. So it's probably a cell that was discharged further than the rest of the pack. And then when it was charged back up, it didn't behave as well. So this would be an example of those two kind of going hand in hand. All right, so let's talk a little bit more about cell balancing. Basically, with cell balancing, you either add or remove energy from from the high or the low cells. And this is done to try and bring the cells into balance with each other. So if you have a cell that's at 90% state of charge and the rest of your battery pack is at 80, you want to remove 10% state of charge from the cell that is at 90% to bring it in line with the rest of the pack. It can be done by adding or removing energy, but it's typically it would be done more commonly by removing energy, simply because you can use a resistor to just bleed off small amounts of current from them. Lithium battery packs tend to stay, as long as you've got decent quality cells, they tend to stay in balance quite well with each other. And if you're using an intelligent balancing algorithm to go in and just make minor tweaks to the state of charge every time you charge, or every couple of times, every few cycles on the battery, even if it's, once every, week or month or something like that, you don't typically need to waste a lot of energy. It's usually more cost effective to burn that off because you can just use a small resistor. It is possible to charge up weak cells, the lowest cells. But in order to do that, you would have to have some type of a charging mechanism for each individual cell, and that usually gets cost prohibitive in larger cell configurations. There is also an active balancing method, and what that does is it takes energy from the highest cell and transfers that energy to the lowest cell, or transfers it to the rest of the pack. And it's supposed to be a way to reclaim energy. Again, it does require more expensive electronics to do. In most situations, if you have good quality cells, you don't end up saving all that much energy, because even if you do that, the efficiencies usually aren't terribly high in that. And so usually for the cost benefit, unless you're working with really large batteries, it may not be terribly cost effective to do that. That said, there are certain applications where that makes sense. Secondhand electric vehicle battery packs, which are ones that have been used in their primary life for an electric vehicle, and they're no longer good enough to run a vehicle, but they might be good enough to do energy storage. Sometimes that's a good application because those cells are going to be all over the board as far as capacity that they have, and you need to be able to handle failures more gracefully in there. So balancing also usually would happen at one particular location in the battery pack, either on the high end or on the low end. Most applications will tend to use balancing on the high end of the battery pack. And the reason for this is you have to pick a place that you're going to spend a lot of time at. In most applications, like if you're talking about a power tool battery or a cell phone or an electric car, you're going to spend most of your time with the battery fully charged, because when you plug in, you're going to top off the battery. And chances are somebody's not going to take the cell phone or the drill battery or the car off the charger the moment it hits the top every time. And that gives you more time to balance. And if you're using a resistor or some type of dissipative balancing, then it gives you more time. It means that you can go with a smaller balancing circuit, reducing costs. Not every application works like that. There are certain applications where you may want to bottom balance if you're maybe spending more time near the bottom. Hybrid vehicles, for example, is a little bit more tricky because you don't have a charger in those, and so the state of charge ends up resting at whatever it rests at when somebody parks the car. So with a hybrid application, you may need to pick a certain state of charge window, and if the car happens to be parked in that particular window, then it can do balancing, and it just waits for the next time that it's within that range. The balancing, you can continue to use a battery pack even when the cells are not balanced to a certain degree. If if you have a battery pack and you have maybe a 5% difference in state of charge from your highest to lowest cell, you're going to be able to continue to use the battery pack. You won't be able to use the top 5% and the bottom 5%. So it does affect the usable capacity, but as long as you are monitoring the individual cell voltages and you don't overcharge and over discharge cells, you should be okay. If you have a more significant balance issue, let's say that you're at like 40% out of balance, you're not really going to have any usable capacity in the battery though. So the purpose of balancing is to increase the usable range. And on this slide here, this shows an example of why that's useful. So in this example, we have a red cell and a blue cell. The red cell is charged higher than the blue cell is, and you can see in the middle section, the middle 100 amp hours that's listed here is the usable capacity. It's the section between where the blue cell goes up and reaches the maximum and the red cell drops to the minimum. If you were charging your battery pack and you would have to stop charging the moment that that blue cell reaches the maximum cell voltage. But yet on that side, the red cell has a left on that side, even though you can't access it. On the discharge side, likewise, you have to stop discharging when the red cell reaches its minimum, even though the blue cell still has more capacity in there. So what you would want to do in this example is either remove energy from the blue cell, add energy to the red cell, or transfer energy from the blue cell to the red cell. And then the goal would be to shift these over so that they line up, and then you would be able to access all 180 amp hours in this example. This is a real-world example of a cell balance issue. In this particular example, the green cell is at a higher state of charge than the red and the blue cells. You can see when at the end of the graph here, we had to stop discharge as soon as the blue cell reached its minimum. So you don't really get to see that last part of the green. But if you could, it would be the exact same shape as those other cells. And then, what we would be trying to do is to shift that over. And again, you'd want to remove energy from the green cell or add it to the rest, add energy to the blue and the red, or transfer energy around in order to maximize the usable capacity. So here are some of the common causes that we see, at least, as causes of battery failure. First of all, low quality cells. As I mentioned before, if you start off with a cell, there's nothing that we can do to add to make the cells magically better than they were originally created. So if the cell, if it's a low quality cell to start with, it's going to pose problems. And if it's a low manufacturing quality, you may develop internal shorts, you may develop early capacity loss or high resistance. If it's a bad cell to start with, it's going to be problematic later on. Allowing overcharge or allowing over discharge, both of those shave life off of cells very, very quickly. Over discharge in particular, you can kill an entire lithium battery pack in one single cycle by over discharging. Those ones you want to watch out for very carefully, and again, that would be a role that a battery management system would play. Using the cells at elevated temperatures, as I mentioned before, it's an exponential function, and it's the type of thing where I'm just going to throw these numbers out there. These are not necessarily good reference numbers, but if you have a battery pack that that might have 3,000 cycles when it is running at 25 degrees Celsius, that same battery pack may only get 300-400 cycles if you're running it at 50 or 60 degrees Celsius, which would be very, very close to the maximum for most cells. So elevated temperatures, even if you're not using the cell at those temperatures, it causes them to degrade faster just from them sitting in those environments. Charging cells below their minimum temperature or charging them too quickly below their minimum or near their minimum temperature is something that can shave a lot of lifespan off. In fact, charging at high C rates in general, C rate is basically the amperage versus the size of the cell. So 1 C would be, if you had a 10 amp hour cell, 1 C would be charging at 10 amps. So it's just a way of measuring the amperage versus the size of the cell. But if you charge at really high rates compared to the size of the cell, that's something that will take life off of the cell. Likewise, using the cell above its maximum currents, specified currents, or using them at their maximum currents for prolonged periods of time also shaves a lot of life off of cells. If you have basically when you're running them at high currents, it, among other things, it generates a lot of heat, and heat is something that is detrimental to the cell, to the life of the cell. So even if a data sheet says that you can draw 10 C or 5 C or 2 C out of a cell, if you do that continuously, you're not going to get, most of the data sheets would specify lifespan in a 1 C charge and a 1 C discharge, or they'll give you the specs, or maybe it'll be 0.2 C charge and a 1 C discharge. When you start drawing more current from them, the lifespan, again, goes down exponentially. So here's some different strategies for detecting faults with cells. I mean, obviously, if you've got voltages that are going up and down, you can get some idea that there's some faults there. The first two here on this list are very helpful as well. Monitoring the internal resistance of the cell. You can sometimes do this in certain applications if you have lots of changes in current. You can monitor, you can measure the change in voltage versus the change in current, and you can determine the internal resistance of the cell by looking at the difference there, though, just using Ohm's law. That's very helpful because if you have a cell that is going bad, in general, the resistance of that cell is going to go up. When the resistance of the cell goes up, it generates more internal heat. And those are things that can be detrimental. If you have lithium plating on the cell, your resistance of the cell is also going to go up. So those are things to be monitoring. Likewise, monitoring the cell capacity. If you have a cell that suddenly has dropped significantly in capacity, you know that there's some type of an issue. It might be just that you have something out of balance, but it might also be indicating that there's a real problem with the cell. And again, those cells can generate a lot of heat, and you don't want to keep using cells that are going bad. It's important to replace them, so to prevent a more catastrophic failure. Cell temperature is another indication. You can monitor temperature. This is a more difficult one. I mean, if you see cells in the battery pack that are significantly hotter or reasonably hotter than other cells in the battery, you know that something is going on, because it's either going to be resistance at a bus bar connection between cells that's gone high resistance or something, or corroded, or whatever the case may be, or the internal resistance of the cell is generating more heat. So if you have a hot spot in the battery pack, you know that something's going on. It is a lagging indicator. It takes a while for heat to build up. That's something to look for there. But it's certainly something to monitor, but it is a little bit of a lagging indicator. When you use these three combined and you monitor the internal resistance of the cells and the temperature, those usually go hand in hand. Usually you can see an increase in resistance and an increase in temperature together, and a decrease in capacity. So using those three together is good. In an automotive setting or in a large format battery, particularly higher power ones, isolation fault monitoring is also very useful to look for breakdowns in isolation between the battery and the chassis or whatever enclosure it's in. That can indicate if there's electrolyte that's spilled from the battery pack. That's usually conductive to some degree, and you can get some type of a reading and that may be something that indicates an issue. Also, it's just good practice, in case you get condensation or metal debris or something like that, or anything that's conductive. It's good to be able to monitor for those types of issues. We definitely see a number of design-related issues where shorts develop, and those are equally problematic as battery problems themselves. The BMS also needs to be monitoring it monitors the battery pack for faults, but it also needs to be able to monitor its own sensors. If there is a problem where the battery management system sensor goes bad and you can't measure the cell voltages, that's obviously going to be a really large problem. Other faults, let's say that you have one thermistor that, or thermal monitoring device, whatever that may be, and it goes bad, you might be able to continue operating without that. The key would be making sure that it goes into some type of a decent fail-safe mode and that you've studied those modes. So here are some just design tips that we've run across. First of all, the battery management system must be able to stop all charging and all discharge from the battery if it determines that it's necessary. Like I said earlier, you can have a battery management system that monitors the battery pack perfectly, but if it doesn't have a way of shutting off the charge and discharge, it doesn't do you a whole lot of good. It's really important to be able to cut off all charge and all discharge, and the reason is that if you have a small trickle charge or a small amount of discharge that's still happening, you can still overcharge and over discharge your battery pack. Trickle, like a small load that's left on the battery, is particularly bad because it can destroy the entire. You can destroy the entire battery pack. But leaving a trickle charge going is something that can lead to a catastrophic failure too. So both of those are important. Ensuring that equal current is getting pulled from each cell is also important. We've seen cases where people have made a battery pack that was maybe 60 cells in series, and then they tapped off the first 4 cells to get 12 volts, so they'd have 2 separate voltages from the battery pack. The problem is that puts unequal wear. Well, first of all, it brings the first 4 cells out of balance with the rest of the battery pack, but then it puts unequal wear and tear on cells. You get uneven heating, just a lot of problems with that. So that's not a good idea. Another thing, to make sure that there is sufficient electrical isolation, everywhere really in the battery pack to prevent shorts. Where that often becomes problematic is if you have like something that's monitoring temperature.